Back again with a little bit more detail of transistor current equations. So the purpose of this section is to provide some insight into the derivation of device equations. They're very, very simple, simplified, but definitely show general trends. The IDS VDS characteristic, or function rather, is going to be characterized in terms of VGS. And we're going to derive it using the charge control model. And that is basically trying to calculate how much charge is in the channel and how much time it takes for that charge to go across the channel. So we're going to start in the linear region with VGS greater than VT, so the device is on. But we're assuming that VDS is quite small, so we have a uniform charge distribution across the channel, throughout the channel if you like. So we start with a very basic equation for how much charge there is in the channel, and it's just minus C times Vg minus Vt. So this is our familiar capacitor equation where Q is equal to CV. So Q sub C is the charge in the channel, that's in terms of coulombs per unit area. Cox is the gate capacitance, and that's farads per unit area. So note the negative sign because the charge in the channel is electrons. We're talking about an N-type device, and Vg minus Vt is the voltage that induces the mobile charge. There's already that voltage before that was required to push holes away and basically not account for charge that's mobile in the channel. The transit time of the charge from the source to drain through the channel is given by this equation here, which is basically the length of the channel divided by the velocity of the charge in the channel. And the velocity is equal to minus 1 times mu n times E, where mu n is the mobility and E is the electric field. So here's another in-class assignment. Which direction do electrons move in the presence of an electric field? So back to the transit time. This is our little cross-sectional cutout of our planar transistor again. And this is the only thing to take note of here. This is L. That's the length of the channel. This dimension over here is W. It's the width of the channel. And there's our old familiar source and drain regions. So as I said in the previous slide, the transit time was equal to L divided by the velocity. And L is the channel length, mu n is the electron mobility, and E is the local electric field. If you like, you could work through this in terms of the dimensions, and you'll see that it turns out to a distance divided by a velocity, so that should give us a time. And in fact, the denominator is the velocity. So now we want to calculate the current equation. Basically, it's the charge in the channel divided by the transit time, and that's really the dq dt, and that's equal to the drain current I sub d. So all we do is plug in those values from the previous slide. The only thing we have to take note of is that we previously calculated the charge in the channel per unit area. So we multiply it by the area of the device, which is W times L. And there's our velocity in the denominator again. So the electric field is equal to Vd divided by L. Very simple approximation for the electric field. And that's just the voltage drop across the channel and divided by the channel length. So there's our equation if we do a little bit of the arithmetic. And we'll see that we have something that at least is looking like it should. It's ID is equal to some function, and then there's some parameter then times VD. So we're in the linear region when VG is constant and above VT. And VD is quite small in this case. W over L can be controlled by the designer, so that might be a parameter that you have some control over, and it basically is associated with the drive of the device. So it's often called beta, or the transistor gain factor, and it's just this term here, mu n Cox times W over L. The only parameters you can play with here, of course, are W and L. Here's a slightly more accurate equation. This term here is the same as we derived from the simple charge control model, and the only thing that's missing on here is the minus Vd squared by 2. This isn't a difficult equation to derive, but we're not going to do it here. You certainly can look it up if you like to. So when VDS is small, the charge control model is reasonably accurate, because when VDS is small, we basically throw away this quadratic term and we get the equation that we got from the charge control model. So these are basically, I would call them zeroth order analytic design equations. They're not very accurate, and certainly not accurate as device dimension scale. But even without that parabolic term, you can still get an estimate of what ID sat might be just from the charge control model by setting VDS equal to VD sat, which is VGS minus VT. And you'd end up with that. And you're really only out by a factor of 2 compared to that more accurate equation. But that more accurate equation is not that accurate anyway. The PMOS, by the way, would just be a direct analog, and as long as you take note of the polarities, you'll be okay. A little bit of discussion on the threshold voltage. It's defined, as we know, the voltage between the gate and the source of a nmos device, below which the current is zero. Well, it's not exactly zero, but we consider it to be zero. The graphs that we looked at previously sort of implied that it was exponential, and that's sort of the source of the leakage current on these devices. For small VGS, initially the charge in the channel is not mobile, as we've mentioned several times, and it's due only to the ionized acceptors. So positive charge on the gate, lines of force end up with on ionized acceptors in the depletion region. Once the minority carrier concentration at the surface is equal to the majority carrier concentration of the bulk, that is, it's as much n-type just under the gate dielectric as it would be p-type in the bulk, further increases in VGS just create a stronger inversion layer. So you just attract more electrons into the channel from the source and drain region. So the threshold voltage can be controlled by modifying the oxide capacitance. Certainly it's something that a designer, you really don't have any control over. It's not a design parameter, and it's really determined by the technology. And this little tiny font here sort of indicates that it's the process engineers at the fabrication facility that are responsible for that parameter. Threshold voltage VT is normally controlled using a threshold voltage implant adjustment, and this is really just materials engineering. I shouldn't say just materials engineering, it's pretty sophisticated. In any event, they are able to basically put in very shallow implants for nmos and pmos devices and adjust the doping concentration so that they can correct the bias to within 10 millivolts or less. But we are going to discuss this a little bit because there are some interesting aspects that are going to show up in a couple of slides. And one is related to this body effect. The body effect is the body voltage. As we know, it's the voltage between the body and the source. It directly affects the threshold voltage, so it's going to be a parameter that you do have some control over as a designer. And this is sort of just talking about older devices were built on a common substrate, but newer devices and those that are silicon on insulator basically don't have an in common substrate, so you have a little bit more control over the body voltage. This is just an example where it might show up in terms of some of the variations on the switching characteristics of a NAND gate. We haven't looked at that in any detail yet, but the only thing to point out here is that the way these are drawn, it's clear to see that the VBS for the P-type device and the VBS for this lower N-type device are equal to 0, whereas this one may or may not be depending on the state of that device. So the body effect is characterized by some equation. This is parametric, if you like, but the important point to note here is, let's say for an N-type device, the body voltage would tend to go up if you increase the body to substrate voltage. So this is the interesting part. On some modern design options within field programmable devices or FPGAs, there's some allowance for various sections of the chip to have a programmable body voltage. In the past, efforts were for regions under the vendor's control, sort of the routing and switching regions, and more recently moving toward regions under the designer's control, where the designer may not know it, as it might be part of the synthesis, sort of where it should be, but these things will take place sort of in the inner workings of the FPGA and optimize so that your design is going to meet its specifications. So this provides another level of power management. In fact, you can increase the body voltage locally, and you end up reducing the leakage current and hence reduce power consumption, and as a consequence reduce heat dissipation. This is a schematic I more or less took from this FPGA Challenges and Opportunities at 40 nanometers and Beyond by Betts and Brown. It sort of shows that within the Quartus 2 CAD software system, which is what you're using, depending on the part, you can automatically reclaim some power by setting tiles that do not contain critical paths to low power state. So these are basically big chunks of lookup table areas, and if they're not on the critical path, you can increase the body voltage there to make them lower speed and lower power, as opposed to being high speed and higher power. And they sort of report it, the increases in the delay would be 20%, but the reduce in the leakage current by 2.5x. So this is sort of how it looks schematically. Here's an N-type device. If you want high speed, you connect the body to 0. If you want low power, you increase the body to something less than 0 volts, in which case then you increase the threshold voltage for that device. So you make it slower and you but make it less leaky. So there's a partial summary up to this point in time. We looked at the basic theory of transistor operation. structure and characteristics of both the nmos and pmos device, operation of at least the nmos transistor in both the linear and pinch-off region, a simple derivation of the device current equations, a little discussion on the threshold voltage and body voltage, and sort of see how these become parameters under your control, which weren't all that long ago. And we'll take a quick break.